Thank you very much, Peter. Thank you to all the organizers for this wonderful conference, and to Doug, of course, for giving us a reason for it. And thank you for this invitation. It's quite an honor for me to be speaking here today. So I'll be talking mostly about the Honeymoon Oberwolfach problem, some of which is joint work with two formerly undergrad students, Danny Lepine and Mary Rose Gerard. I will have to get through some sort of an introduction to the Oberwolfach problem before I can talk about my main focus here. And forgive me for maybe duplicating some of the things that this morning's speakers have already said, Andrea, Melissa, and especially Peter. But I will try to go through this part fairly fast, but not too fast. And then my main focus, as I said, will be the Honeymoon Oberwolfach problem. So a quick introduction into the terminology here. So we say that a graph is decomposed into its subgraphs, H1 through HT, if its edge set is partitioned into the edge sets of these subgraphs. So here's a picture. We have the complete graph on 8 vertices, and it's decomposed into several copies of, I think, a 4 cycle, as well as a 1 factor. Unfortunately, I have something in the way here. Okay. So think of this as coloring the edges of G so that the color classes represent these subgraphs. Okay, we have a thick red 1 factor, and we have a yellow 4 cycle and a blue 4 cycle, and so on. If all of these subgraphs are isomorphic to a single graph H, then we talk about an H decomposition of G. And in particular, I'd be interested in cycle decompositions. So CM decomposition is a decomposition of a graph G into copies of a cycle of length M. And the picture here shows a C3 decomposition of K7, which is known by design theorists as a Steiner triple system on 7 points, and also as the Fano plane to those in finite geometries. Most of my cycle decompositions will actually be resolvable. So let me talk about 2 factorizations. So as everybody knows, an R factor is a spanning R regular subgraph, and so a 2 factor is a disjoint union of cycles. And often I'll want to specify the type of this 2 factor. So I'll call this a CM1, CM2 through CMT factor when we have a disjoint union of cycles of these given lengths. The lengths may be repeated. So in the picture below, you see a C3, C4 factor in K7, I believe. And a factorization into these 2 factors of the given type will be called a CM1 through CMT factorization. So again, a picture shows a C3, C4 factorization of K7. When all these cycles of the same length, I'll be talking about a CM factor. So that's a 2 factor that is a disjoint union of cycles of this length M, and the number of cycles depends on the order of the graph. So again, the example shows a C3 factor in red, and overall a C3 factorization or decomposition into C3 factors. We can think of this as equivalent to a resolvable CM decomposition. The parallel classes correspond to the 2 factors. And this is also called a resolvable Steiner triple system on 15 points, or a Kirkman triple system on 15 points. Okay, so going right into the Oberwolfach problem. So we've heard this before, but just in case you've missed it. So posed by Ringel in 1967 at a conference in Oberwolfach as this kind of a seating or scheduling problem. We have an odd number of participants, and we'd like to seat them for K consecutive nights so that everybody gets to sit next to everybody else exactly once. And we have tables of given length, and the total number of seats available is precisely the number of participants. So this can be modeled as a 2 factorization of a complete graph. Here is the arrangement on the first night. We have a table for 3 and a table for 4, and the colored edges are those pairs of participants that have already used up their ticket for that night. And then we can have the arrangement on the second night, again, a 3 cycle and a 4 cycle, the 2 tables, and the third night, we have the remaining pairs occurring there. A complete graph of even order has odd degrees, so it does not allow a two factorization. And so the easiest way, or the closest that we can get, is the complete graph minus a one factor. So we delete a one factor and we think of these edges of the one factor as corresponding to the K couples, so that the spouses in a couple never get to sit next to each other, but get to sit next to everybody else exactly once. And again, we have table sizes available. So here's now a solution to this problem, the spouse avoiding variant with tables for 3 and 5. So the first, the second, and the third night. Both of these variants are denoted by OP, M1 through MT, the M's being the table sizes or the cycle lengths. And we're assuming that the obvious necessary conditions are satisfied so that the number of participants is exactly the sum of the cycle lengths. And we're asking whether the complete graph or the complete graph minus a one factor, depending on the parity of n, admits a two factorization of this specified type. So the picture here shows a solution to OP 3,5. 3 plus 5 is even, so that's the spouse avoiding variant. The notation for the uniform cycle length is can be simplified to n semicolon m. N is now the number of participants or the number of vertices, and m is the length of the cycle. So assuming that m divides n, which is an obvious necessary condition, does there exist a CM factorization of the complete graph or complete graph minus a one factor? And here's a solution to OP. This would be 15 semicolon 3, also called Kirkman triple system. And even though I've mentioned before the problem was first posed in 1967, it actually goes back further to 1850 when Kirkman first posed the so-called Kirkman schoolgirl problem in this very colorful way. He says 15 young ladies in a school walk 3 abreast for 7 days in succession. It is required to arrange them daily so that no two shall walk twice abreast. And so we're looking for a collection of triples, the rows of 3 out of the 15 girls, so that every pair of elements girls are in the same row, or exactly one triple, exactly once. And in addition, we want these triples to be partitioned into subsets of 5 pairwise disjoint triples, these parallel classes, or the days when the 7 days in succession. This was a very exciting problem for the times, and Cayley got the first solution, and then Kirkman himself, and then more solutions were found, and 7 non-isomorphic solutions by Woolhouse, and then it was even proved that these are precisely all of them. And the solution that I gave on the previous page is actually the first solution given by Cayley. Now, by now, and in fact, by the 1990 so, the complete solution to the Oberwolfach problem with uniform cycle lengths was known. So we know that it has a solution if and only if the necessary conditions are satisfied, except for these 2 special exceptions, when we have 3 cycles and 6 vertices, or 12 vertices. These are both spouse avoiding variants. The first contribution was by Jiaxi in the 1960s, but his papers actually were not known until the 80s, after the independent solution by Rachel Dorian Wilson in the 1970s. That's for the triples with the number of vertices odd. The spouse avoiding variant for triples was given in the 70s and 80s, and here you will notice Doug Stinson's name for the first time. It will occur a number of times in this talk. The even cycles were considered by Alsbach and Hackfist, and then the odd cycles, again, a contribution by Doug Stinson. Notice one exception here, odd cycle length with 4 tables. This was not solved in this paper, but was later filled in by Hoffman and Schellenberg in 1991, I believe. For some reason, I can't see this line there. Okay. The Oberwolfach problem for variable cycle length is actually still open in general. There are 4 cases known where there's no solution, the 2 with uniform cycle lengths, and then 2 more, 4, 5, and 3, 3, 5. And it is widely believed that these are the only exceptions. As we have seen before, the uniform case has a complete solution. It's also known that OP has a solution for infinitely many orders and for any admissible two-factor types. Also for all small orders. This is a bunch of papers that involve these authors here. For bipartite two factors by Bryant and Danziger. For two tables by Trietta. For all sufficiently large orders, that's the asymptotic result that Peter was talking about, where we don't actually know precisely how large this n needs to be, potentially very large. And finally, we have a solution for a very recent solution that Peter was talking about for single flip two factors with one sufficiently long cycle. So that's a result by Burgess, Danziger, and Trietta, just published this year. And even though I'm saying sufficiently long cycle, this is not truly asymptotic in that they actually give a lower bound. So we know precisely how long this cycle has to be. All right, now, Peter also mentioned that there's another way to deal with an even number of participants. So instead of removing a one factor when the number of participants is even, which would amount to packing the complete graph with as many two factors as possible without overlapping. In other words, this could be considered a maximum packing variant. So instead of that, we can actually duplicate a one factor. In other words, we're trying to cover all the edges of the complete graph with one factors so that there's as little duplication as possible. What does get duplicated is this one factor I. Okay, so this can be seen as a minimum covering of the complete graph. And I like calling this the spouse-loving variant because now the spouses, these couples correspond to these specific one factor, and the spouses will get to sit next to each other exactly twice, excuse me, instead of not at all. So what's known about the spouse-loving variant? Not nearly as much as on the original two variants. So the notation is OP plus, and the rest is similar to the original variant. We do by now have a complete solution to the uniform case. We have exactly the same two exceptions, 3 cycles with 6 and 12 vertices. And as we have seen before, the first contributions to this were by Asaf Mendelssohn and again Stinson, as well as Lampkin and Mills that covered the outstanding cases. This was for triples, and the result was actually published under the name Resolvable Minimum Coverings by Triples. And then not so long ago, Andrea Burgess and I, with our undergrad students, Bolahan, Buchanan, and then Snick, looked at the more general uniform table case. So in this paper published in 2019, we were able to complete the even cycle length, as well as the odd cycle length case, except the case of 4 tables of odd length. And this will sound familiar from the original Oberwolfach problem. This outstanding case was actually just very recently filled in by 3 Indian mathematicians, Vadivu, Panirselvam, and Muthusamy. So they were able to complete the solution then. Not much is known about the variable cycle length. No exceptions are known in these cases. The uniform case has been solved, of course. We were also able to well, essentially, this was a corollary to the result by Bryant and Danziger, namely that we have a complete solution for even cycle lengths. And as Peter mentioned, their paper just published this year also covers the spouse-loving variant for single flip 2 factors with one sufficiently long cycle. And I think that this result will be quite far-reaching. So we'll see more probably coming out of it later. It was at the time when I was working on the spouse-loving variant that I came up with this idea. Well, okay, so we have these loving spouses, but what if they're actually really crazy about each other and want to sit next to each other every single time, not just twice, but every night? And at the same time, they also want to get to know others and sit next to everybody else exactly once. So that was the idea behind the Honeymoon Oberwolfach problem. And you can see that the name comes from the fact that we can consider these couples as being newlyweds. And so that's why they want to sit next to each other all the time. Okay, so we've got two N participants, that is N couples, N newlywed couples, and we want them to seat them at T round tables of specified lengths. The number of seats is exactly right. Everybody gets to sit next to everybody else exactly once, except they sit next to their spouse every time. Can this be done? Here's an example with three couples. So AA, BB, and CC are the three couples. And let's look at the arrangement on the first day. So this is the case with one table for 6. So we can see that the couples sit next to each other. And then some other pairs are also covered. And here will be the second night. Again, the couples sit next to each other and some other pairs are covered as well, and so on. So by the time everybody has been seated next to everybody else exactly once, except their spouses, we have obtained a 2 factorization of the complete graph plus a few extra copies of the special 1 factor. This 1 factor corresponding to the couples. In this particular case, we had a 4-fold 1 factor I, so 3 additional copies added to the complete graph. All right, so we're looking at a 2 factorization of a specified type of the complete graph on 2n vertices plus, now there are 2n minus 2 participants that are not in my couple, so 2n minus 3 additional copies of this 1 factor. But our 2 factors have to be of a particular kind. Every cycle has to be I alternating. That means that every second edge comes from this particular 1 factor I corresponding to the spouses, okay? Which also means that all of the cycle lengths have to be even, because spouses always sit at the same table. So I'm denoting this problem by HOP, M1 through MT, these being the cycle lengths. And in case of a single table size 2m, has to be even, I'm going to abbreviate this as 2n semicolon 2m, just following the notation for OP. Now, here's a solution that we found before, but you may be saying, oh, wait a minute, but this is really just a 1 factorization of the complete graph. So if we shrink our multiple copies of I back into a single copy, then what we have here is just a 1 factorization, but not any 1 factorization. It is of a specific type, it's a specific kind, namely that this gray 1 factor union every other 1 factor, the colored ones, gives us a 2 factor of a specified type. In this case, type 6. In other words, we have a single cycle of length 6. So these kinds of 1 factorizations can be called semi-uniform. So a solution to HOP is equivalent to a semi-uniform 1 factorization of the complete graph of order 2n of type M1 through MT. So the type is precisely the type of the 2 factor. All right, so that's the definition of a semi-uniform 1 factorization. We have a 1 distinguished 1 factor, and its union with every other 1 factor has to be a 2 factor of a specified type. Now, there are other kinds of special 1 factorizations. A semi-uniform factorization in which the type is a single Hamilton cycle is called semi-perfect. So the union of the distinguished 1 factor with everybody else is a Hamilton cycle. And these 2 terms are a relaxation of the better known terms uniform and perfect 1 factorization. So a perfect 1 factorization is a 1 factorization in which the union of any 2 1 factors is a Hamilton cycle. And when the union of any 2 1 factors is a specified 2 factor, and that's called uniform of the given type. There's another relaxation of these 2 concepts, namely sequentially uniform and sequentially perfect. So in this case, we have a cyclic ordering of the one factors, so that the union of any two consecutive one factors in this cyclic ordering is a specified two factor. And if this specified two factor is a Hamilton cycle, then we're talking about sequentially perfect one factorizations. What's known about these? So you may have heard of Kotzik's conjecture, posed in 1964 by Kotzik, which says that every complete graph of even order admits a perfect one factorization. This conjecture has been confirmed for many orders, but it's in general still open. And I believe we'll hear more about this later this afternoon. Kralevich and Kralevich coined the term semi-perfect one factorization, and also showed that any complete graph of even order admits a semi-perfect one factorization. And then Dinitz-Duke and Doug used the term sequentially perfect and proved that the complete graph of even order admits a sequentially perfect one factorization, again, for every even order. As you'll see shortly, we were able to extend the result by Kralevich and Kralevich to all semi-uniform one factorizations. Now here is the complete result that we were able to get in this paper. So HOP 2M1 through 2MT has a solution, first of all, in the case that all cycle lengths are the same, so the uniform case. So that's one big case solved. The other one, and I'll skip right down to the bottom, is the case of small number of couples. First, in the paper that I mentioned here, we proved that it has a solution for up to 9 couples. But more recently, with Mary Rose Gerard, we improved this to up to 20 couples. And this extended result is partially done computationally. The results 2 to 5 are all primarily consequences of solutions known to the Oberwolfach problem, except that we had to fill in a few exceptions. So we know that if the order is odd, if the number of couples is odd and OP has a solution, then HOP with twice the cycle length has a solution. We also have a solution when all of these MIs are 0 mod 4. That's the consequence of the bipartite solution to OP. When N is odd and we have exactly 2 tables, and also for all small and odd numbers of couples. That's due to the solutions to OP with small orders. So a corollary to the first statement here is that any complete graph of even order admits a semi-uniform one factorization of any type. So any type when we have all cycles of the same length. For the remainder of the talk, I'd like to tell you a little bit about the approach that we took here and give you sketches of some of the proofs. So going back to the example that we had, so we have 3 couples and a table of size 6. Let's look at an example of such a table. Notice the one factor here covered. So what we do first is we're going to put all the men on the left and all the women on the right. And we will color all the edges between men blue and the edges between the women pink, and the edges that go from a man to a woman by black, and will direct it from the man to a woman. And I apologize for the stereotyping here, but it's just so convenient. Now, notice that the gray edges between the spouses, those, of course, we know are present, so we really don't need to carry that over. So we go to identify the couples into a single vertex. So couple now becomes a single vertex. And notice that we got this cycle of half the previous length, so cycle of length 3 now. Now, another example of a table, we get the following cycle with that, which then condenses to a black directed cycle. Okay, so in general, when we have couples X, X, and Y, Y, we first color the edges, blue edges between the men, pink edge between the women, black edges from a man to a woman in a different cycle, gray edges between the spouses, And then we identify the couples, the spouses in the couple. And what results from these 6 edges here are just 4 edges, 4 parallel edges, 1 pink, 1 blue, and 2 black, oriented in opposite ways. Okay, so this is how we get from the original graph to the 4-fold complete graph. But it's not just 4-fold, it's also color oriented in this particular way. Now, what happens? So this is now the example. We color all the edges and then we condense it to the 4-fold color oriented for K3 in this case. But what happens to our cycles? So let's look at sort of an arbitrary cycle in the original graph. As we move along the edges, we will see that a blue edge, for example, can be followed by a pink edge. It cannot be followed by another blue edge because blue edges are on this side only. Okay? It can also be followed by a black edge, but this black edge will be directed towards the blue edge. Similarly, a pink edge can be followed by a blue edge or by a black edge, but the black edge will necessarily be directed away from the pink. And a black edge can be followed by a black edge, but they will have to be in the same direction. So the condensed cycle therefore looks like this. It will have runs of blue and pink edges alternating. It will have runs of black edges oriented in the same direction. And this direction will always be from pink to blue. Okay, this is a necessary and sufficient condition for these condensed cycles to be able to be liftable back to into the original graph. Okay, to summarize this, by an HOP coloring orientation of a 4-fold graph G, and I think of G as a simple graph, we mean a 3-edge coloring of this 4-fold graph, and the edges are pink, blue, and black, as well as an orientation of the black edges, so that every 4 set of parallel edges contains 1 pink, 1 blue, and 2 opposite black arcs. And I'll put this dot here for the 4-fold G to denote that I already assumed that it has this HOP coloring orientation. And we'll call a 2 factorization an HOP 2 factorization of the 4-fold graph G, if in every cycle, every 2 adjacent edges satisfy one of these properties, the properties that we just observed, namely that for any 2 adjacent edges, one is blue and one is pink, or they're both black and directed in the same way, or one is blue and one black, and the black is directed towards the blue, or one is pink and one black, and the black is directed away from the pink edge. And then it's not so hard to show that HOP with cycle lengths 2m1 through 2mt has a solution if and only if a 4-fold graph Kn, so 4Kn dot, has an HOP 2 factorization with half the cycle lengths. So the cycle lengths get halved, and of course the number of vertices also gets halved. So that means that all we need to do to solve HOP is to find an HOP 2 factorization of the 4-fold Kn, n being the number of couples that we started with. So for example, for the example that we've seen before, HOP 6, a single cycle of length 6, we have condensed our graph to 4-fold K3 dot. And now we can start with the first 3 cycle. This is obviously an admissible cycle because we have blue and pink alternating, and then we have a black edge going from pink to blue. Okay, so that's the first one. Now, if we rotate this one, we haven't overlapped any of the edges yet, and we can rotate again, and again, no overlapping. At this point, so notice that I'm showing down here what the corresponding cycle is in the original graph at the same time. So here's this one and the third one. And at this point, all that we have left is the 3 black arcs, which give us a 4th admissible cycle, a directed black cycle. So this gives us a solution to HOP 6. Now, in general, how can we approach this? Well, the easiest case is when we have a simple graph G that itself admits a two-factorization of the desired type. Okay, so in that case, we can show easily that fourfold G dot also admits an HOP two-factorization of this same type. And if you think for a second, you'll realize that it's enough to show that this is true when G is a cycle itself. So when G is an even cycle, we can then construct a fourfold, an HOP CM factorization of the fourfold CM as follows. We'll have two copies of this cycle that alternate pink and blue in two different ways. And then we'll have two black cycles that are directed in opposite ways. And so this way we have covered each edge in quadruple. So pink, blue, black forward, and black backwards. When the order is odd, it is similar. We just need to make a little bit of an adjustment in two edges here at the end. So most of it is alternating and directed black as before, but then we have to make the adjustment in these two edges here, and you can verify that this works. A quick corollary of this result is the result that a solution to HOP with twice the cycle lengths follows from a solution to OP with cycle lengths M1 through MT, assuming that the sum of the cycle lengths is odd. So if OP M1 through MT has a solution and the order is odd, that means that the complete graph admits a two-factorization of this specified type. And so by the previous lemma, the fourfold complete graph admits an HOP two-factorization of this type, and that gives us a solution to HOP with twice the cycle lengths. All right, so that's the easiest case when we can use previous decompositions of complete graphs. Notice that a solution to OP with even order is not helpful because a two-factorization of Kn minus one factor will not be helpful in this case. Now, the next easiest case is when we have a two-factorization of a specified type for the twofold graph G, where G is, again, a simple graph. Normally, this will be the complete graph. However, a little bit more is needed in this case. So in addition to this two-factorization, we also need to have a two-edge coloring. I'll use the colors black and pink here, so that every pair of parallel edges contains a black and a pink edge. In other words, we're looking at a pink and a black copy of G, if you wish. And then in addition, every cycle of length at least 3 must contain an even number of pink edges. So if this is the case, then we can double this original two-factorization of 2G to get an HOP two-factorization of the fourfold graph G with the same two-factorization type. So I'll show an example of how this works. So what you see here is a starter two-factor for the graph 2K10, so a twofold complete graph on 10 vertices. We have one vertex in the middle. Think of this as our infinity vertex or fixed vertex. And then we're going to rotate this starter to obtain a complete two-factorization. Notice that each edge, or rather each difference occurs twice here. So difference 1 here on top and 1 at the bottom, difference 2 here and here, difference 3, difference 3, difference 4, difference 4, and we can think of the edges incident with the infinity vertex as difference infinity. So each occurs twice, and so when we rotate this all the way around, we'll get each edge exactly twice. Okay, but now we need an appropriate two-edge coloring. So let's try this one here. So we need colors pink and black, and we need each difference occurring in a pink and a black incarnation. So we have a pink and a black difference 1, we have a pink and a black difference 2, difference 3, and difference 4, as well as infinity. Okay, and in addition, we have that the cycles of length at least 3 contain an even number of pink edges. So we have 4 for this cycle and 0 for the black cycle. And we don't care at this point what happens with the 2 cycles. So the next step then is to recolor this in 2 different ways. And what we do is we recolor every second pink edge blue, okay, in 2 different ways. So over here, we started with pink, blue, and so on, and over here with blue, pink, and so on. So this is for the long cycles. For the cycles of length 2, we'll simply have it in 2 copies. One will be pink and blue, and the other one will be black. And then finally, we need to orient the black edges. So in this case, we simply orient the each black cycle so that it becomes a directed black cycle. And we do that in 2 different ways for the long cycles. And for the cycles of length 2, there's just one such cycle, so we orient it so it's a directed 2 cycle. Now, we could have done this in a different way, though. We could have started with this sort of a 2-edge coloring. So now we have, again, that each difference occurs in the pink and black copy, but each of the 2 long cycles have 2 pink edges. And so again, recolor every second pink edge blue, and then appropriately orient the black edges so that the cycles have this HOP property. Okay, notice that we have pink and blue alternating, and black arcs always go from pink to blue. Okay, now a quick corollary to this lemma will be the result for cycle lengths that are divisible by 8. So these MIs are all divisible by 4. And that's a corollary of the OP result for bipartite 2 factors by Bryant and Danziger. So we know that if the cycle lengths are all even, the complete graph minus a 1 factor admits a 2 factorization of this type. Now let's take 2 copies of the complete graph, a black and a pink copy. And we're going to strategically choose a 1 factor, a black and a pink 1 factor, so that their union is a 2 factor of specified type. We can always do that because the cycle lengths are even, right? So this way we get a 2 factorization of the 2-fold complete graph with, and as well as a 2-edge coloring, so that every pair of parallel edges contains a black and a pink edge. And in addition, notice that every cycle, every cycle, in fact, will have an even number of pink edges. This number is either 0 if that's a black cycle coming from a black copy, or it's going to be the same as the cycle length if it comes from the pink copy, and that cycle length is of course even, or it's going to be half the cycle length if that's a cycle that comes from the union of the 2 1 factors. We know that every other edge in these cycles is pink, and because the cycle length is divisible by 4, we will have an even number of pink edges. All right. So by the previous lemma, then the 2-fold Kn having the appropriate 2-edge coloring implies that the 4-fold Kn will have an HOP color orientation, okay, or an HOP 2 factorization of the appropriate type. All right, now what about the difficult cases? Not all cases fall into one of these 2 options. We may not have an appropriate 2 factorization of Kn, or even of 2Kn, or if we have it for 2Kn, it may not admit an appropriate 2-edge coloring. So what do we do in those cases? I'd like to tell you a little bit about the most difficult case. And this will be the case, the uniform table case with odd table sizes. So here's a reformulation of the result. So HOP with the uniform cycle length has a solution if and only if M divides N. So the cycle length divides the number of participants. The necessity is of course clear. We need the number of vertices to be divisible by the length of the cycle. So I'll just indicate or give you a sketch of the proof of sufficiency for odd cycle lengths and M at least 5. The 3 cycles have to be dealt with in a slightly different way. The even cycle length, the approach there is quite similar, but the base case is much easier and relies on previous results. So for odd cycle length, the base case is one of the most difficult cases. So assume that M divides N. Now, in case that N is odd, then we're looking at an odd number of vertices in our fourfold Kn. And we know that in this case, OP has a solution. And so by the previous result that we've just seen, HOP with twice the cycle length has a solution as well. So it's sufficient to look at the cases where N is even, number of couples is even. By T will denote N divided by 2M, so that's an integer now, of course. We'll first assume that we have a solution when T is equal to 1 and when T is equal to 2. The first is our base case, and the second one is an exception that has to be dealt with separately. So assume that this multiplier T is at least 3 for now. We will first decompose our complete graph on N vertices in T copies of K2M in blue here, and the complete equipartite graph with T parts of size 2M, the orange graph here, so the edges between the parts. Now we have, by the assumption, by our base case, we have that the fourfold K2M dot admits an HOPCM factorization, and we'll see this shortly how that works. So that's done. Now, what about the complete equipartite graph? Well, by a result by Liu that I think Andrea mentioned before, it admits a CM factorization because each part has size 2M. And so by our previous lemma, of our first lemma, in fact, the fourfold complete equipartite graph admits an HOPCM factorization, and we're done with this part as well. So what remains is to look at these two exceptional cases, the base case and the exception. So the solution to the base case looks something like this. So what you see here is 2 starter 2 factors. Each has 2 M cycles. We have an infinity vertex that is from me down below where I can't see it. So that will be the fixed vertex. The rest of the vertices will be rotated. And similarly over here, infinity vertex fixed and the rest is rotated. And now the way that these 2 starters were color oriented is that each difference occurs exactly 4 times between the 2 starters. One's pink, one's blue down below here, one's black forward, and one's black backwards. If we look at difference 1. Difference infinity, for example, here's pink, here's blue, there is black oriented towards the infinity vertex and black oriented away from the infinity vertex. So that means that when we rotate each of these starters, we will cover each edge exactly 4 times, pink, blue, black forward, black backwards. This is for the case when K is even. When K is odd, we have a similar construction, but it does have to be done in a slightly different way. But the idea is the same. So that covers the base case. Now, what about this exceptional case? This was a little bit easier because we had a CM factorization of the 2-fold complete graph given by Gvozdiak. And so all we needed to do was appropriately 2-edge color it. Here's an example for 5 cycles. So we have 4 5 cycles giving us a starter 2 factor for 2K20. We first color it in pink and black so that each cycle has an even number of pink edges, and so that each difference occurs twice, once black and once pink. And then we recolor in 2 different ways, recolor each second pink edge blue in 2 different ways. And finally, we orient the black edges appropriately. That can always be done then. And so this gives a solution for the fourfold K4M. All right, so we have covered the two special cases. We have the reduction part, and therefore we have that 4kn dot admits an HOP CN factorization for all n divisible by m, and HOP with uniform cycle length has a solution. Okay, so summarizing again all of the results that we have here: uniform cycle length, small orders, and then these additional results that come from using solutions to OP with additional tools, as well as filling in the exceptions to OP. And here I remind you again that solutions to OP, there are a number of small exceptions, but you don't see any exceptions here to HOP. That's because there are none. We do not know of any exceptions whatsoever, which makes me conjecture that the obvious necessary conditions for HOP to have a solution are also sufficient without any exceptions whatsoever. And as you can see, we have a lot of evidence for that. Now, what is left to do? So these are some of the things that I'd like to attempt in the future. First of all, I think we can do better for bipartite two factors. So HOP 2M1 through 2MT, where the MI are even, so that in the condensed graph, we're looking at bipartite two factors. So we have a complete solution for MI being divisible by 4, but I think we can do better. I also think we can do better for the two-table case. So we have a solution when the number of couples is odd, but I think we can do it for the even as well. Because of the result by Trietta for the twofold complete graph, admitting two factorization into two factors consisting of exactly 2 cycles. So there is an exception here, but the rest, there is a complete solution. So I'm hoping that we can use these two factorization and then appropriately to edge color them. And then finally, I'd like to look at the case, the kind of extended HOP, where we're allowing tables of size 2. So allowing tables that would sit precisely one couple and nobody else. Some of these cases will then be a PhD project for my student, Massimo Akbari, who hopefully is listening here right now. I'd like to say a little bit more about the case of tables of size 2. So suppose we have an example with 4 couples and 2 tables, a table for 2 and a table for 6. So here would be an arrangement on the first night. So the couple AA will sit at their own table for 2. And then on the second night, we'll have again the same couple at the table for 2. And then on the third night, couple BB has its own table, and then again BB, and then CC, and then CC again, and then DD and DD. And by now we have covered every pair of participants exactly once, except that the couples always set together. Notice that we have now a decomposition of the complete graph K8 plus a few extra copies of this one factor into subgraphs that are not 2 factors anymore, but rather each of these graphs is a disjoint union of K2 and a cycle of length 6, or if you wish, a path of length 1 and a cycle of length 6. So that means that if we choose the same approach as before, that once we condense our graph, and we obtained in this case a 4-fold K4 dot, then we're looking for a decomposition of this 4-fold K4 into subgraphs, in this case, consisting of just a 3 cycle. So the path, or K2, if you wish, or the table for 2, will shrink into a single vertex. And then what we'll have left is a cycle of length 3 coming from the table for 6, okay? So that means that what we need to do is find an HOP C3 decomposition of this 4-fold complete graph of order 4, in this case. The easiest case would be if we can decompose K4 into 3 cycles, but of course that's not possible because it has odd degree. The next best would be if we can find a C3 decomposition of the 2-edge colored twofold K4, so that these properties that we established before hold. And indeed that is possible. So here's an example, a decomposition into these 4 3 cycles, and notice that every cycle has an even number of pink edges. And then as before, we're going to recolor each of these in 2 different ways, replacing every second pink edge with a blue edge, and then appropriately orienting the black edges. So here is then a solution to HOP26. Now, in general, there are some results that can be used in our favor. So suppose that we have the HOP with S tables for 2, and then the remaining tables will be longer. So these M1 through MT are each at least 2, which means that we get tables for 4 and more. So as we have seen, a solution to HOP with these tables is equivalent to an HOP CM1 through CMT decomposition of the 4-fold complete graph of order n. So a decomposition into 2 regular subgraphs of a specified types consisting of disjoint M1 cycle through MT cycle. And because we're looking for this decomposition, we have a necessary condition that the number of edges in each of these 2 regular subgraphs divide the number of edges in the 4-fold complete graph. So as mentioned before, the easy cases are the ones where a decomposition into these 2 regular subgraphs of the complete graph itself exists. And here we'll be using results on decompositions into cycles. There's a complete solution. Decompositions into subgraphs that consist of 2 disjoint cycles. We have some results there. Into subgraphs that consist of disjoint M cycles, so the uniform case. And also there are some results on 2 regular subgraphs of small order that we'll be able to use. More involved will be the cases where a decomposition of the complete graph does not exist, but a decomposition of the 2-fold complete graph exists. So here are some results, namely for the 2-fold complete graph and decompositions into cycles. In other words, 2 regular subgraphs that consist of a single cycle. And we also have results, or rather there exist results on the uniform case. Here, of course, we'll also have to find appropriate 2-edge colorings of these decompositions into 2 regular subgraphs. And of course, there will be harder cases as well where neither of those exist, and we'll have to go straight into the 4-fold complete graph. All right, so that's hopefully I'll be able to tell you a little bit about this in a couple of years. And at this point, I will just say thank you all of you for your attention, and happy birthday to Dad.